to computer. Hello, Organic Chemistry 2330. Here it is, our last lecture of the semester. Oh, anyway, there will be a review before our third exam next week. So go ahead and make sure you show up on Tuesday for our review. I'm going to start with chapters 8, the last chapters 12 through 16, but then I'm also going to go back through chapters 1 through 11 to make sure that you are remembering really important stuff like hybridization and shapes of molecules and stuff like that. Okay, so that's what we're going to be doing next week. Now, also bring questions, please, because if you have questions or like, what is RNS again, you know, that kind of stuff, that's going to be kind of stuff that we might see on the exam. I'm going to go ahead and I'm going to write the exam over the weekend so that I will know exactly what's on the exam. I won't tell you what's exactly on the exam, but I'll give you the concepts that are on the exam so that you can be prepared to study for those before our exam. Now, our exam on next week is focused on chapters 12 through 16. Okay, so that's the focus of the chapter. However, the final is going to be cumulative, 1 through 16. So it's not a bad idea to kind of start ahead, you know, start of course with their last 4 chapters here, and then move on to chapters 1 through 11. All right, questions on that? All right, I'm not muted and nobody's in the chat room. So let's go ahead and move on. So Tuesday, we learned about polymers, and polymers are just really big molecules that have the same repeat unit over and over and over again. Now, when we started with this, we learned what we called step growth polymers. And they're step growth polymers because one functional group is going to react to the other functional group to link it. So you have 2 of them together, and then another functional group is going to react at that end and link and step and step and step and step and step. So that's why we call them step growth polymers. And they're very commonly seen because they have some kind of functional group in the middle of the chain. Okay, so there's like an amide or an ester or an ether or something like that. There's a functional group in the main part of the chain. Okay, so that's how we can distinguish our step growth polymers. Okay, because they have those functional groups in them. Now I want to talk about a different type of polymer, a type of polymer called chain growth polymers. Okay, now in chain growth polymers, what we see is the formation of a new carbon-carbon bond from a double or triple bond. Okay, so this is where the entire backbone, the entire long part of the polymer, not the substituents, but the entire backbone is all carbon. Okay, so that's distinctly different from those step growth polymers. The step growth polymers will have oxygens and nitrogens and carbonyls in that main chain of the polymer. Chain growth polymers typically only have carbons in their main chain. Okay, now because of that, they're actually polymerized in a slightly different way. Okay. The other interesting thing about chain growth polymers is in all of the step growth polymers, most of the time we lost water or a small molecule of alcohol or something like that. In chain growth polymers, we lose no atoms. Okay, so industrially, they really like them because you put in 100 pounds of ethylene, you get out 100 pounds of polyethylene. And so that's why they really like this, is that it's very efficient in its use of chemicals. Okay, so let's move on and figure out how they are polymerized differently and how we name them differently than other things. Okay, so in the case of common polymers, we take what the common or engineering name is, and we put poly in front of it. Okay, so if we have a monomer formula that looks like ethylene, or which is ethene for our IUPAC name, but ethylene is our common name, then we're going to the polymer made from it is called polyethylene. Okay, so polyethylene is used in the grocery bags that's nice and stretchy. It's used in packing materials. It's also used in very thick bed liners in trucks because it can also support itself really well. Okay, so that's polyethylene. Now, if we add 1 carbon to ethylene and have a little CH3 on there, now we have propene, or the common name propylene. In propylene, all we've added was that one little methyl group, and it changes the properties. It actually makes it very different from polyethylene. The fact it's stretchier, it's tougher, it rearranges more. And so it's used in different things. For polypropylene, it's used in very strong fibers. It's also used in some of the clear bubble packaging you get is sometimes a special kind of polypropylene. Now let's go ahead and change it to put in a chlorine there instead of a methyl group. So now we have a chloride on an ethylene or a vinyl group, that double bond, sometimes called a vinyl group. So we have vinyl chloride, and when we make the polymer of it, we call it polyvinyl chloride. Okay, so naming these polymers is actually kind of cool because it tells you exactly what they made it out of to make that polymer. PVC is like PVC pipes that you see for construction and tubing. It's also used in very soft, flexible pipes, like in a bar where you put kegs on it, you have these transparent pipes. Those are PVC, but they have things added to them to make them soft. Okay. So then if you add another chlorine to it, and so you have two chlorines on the same carbon, you now have dichloroethylene. And this is actually changes the properties. It makes it nice and flexible. And it's typically made with another copolymer. And so think saran wrap, that stretchy wrap you can put over bowls like that. It's also used in some medical devices because you can sterilize it with ethylene oxide. And so it's sometimes used in that as well. Okay. Now the next thing I want to look at is let's change out that chlorine with a cyano group or a nitrile. So we call that acrylonitrile because we would make the nitrile out of acrylic acid. Okay, so it's acrylonitrile. And this little cyano group makes really strong fibers. Okay, so you almost always see these in fiber form, and it's like Orlon, which is one of the fibers used in sporting equipment because it's really tough and really easy, really nice to use. Okay. The next one we have is tetrafluoroethylene, which makes Teflon. Teflon is actually the registered trademark name by DuPont, but the general name is PTFE, polytetrafluoroethylene. Okay, so if you see PTFE, that means it wasn't made by DuPont. If you see Teflon, it was. Okay, it's used in nonstick coatings. It's also used in chemically resistant labware. Okay, and they're typically a really solid white, and they're quite heavy because all the halogens make it denser than most other polymers. Okay, so let's take those fluorines off and put a phenyl group on there. We call that styrene. Remember when we did our chapter on aromatic rings, we called that special one styrene. Styrene is used predominantly in styrofoam. That's a trademark also. It's styrene foam. It's used also as an insulating material, and sometimes you can find it in certain plasticware, like plastic forks and stuff. And you can tell if it's polystyrene because if you break the fork and sniff it and it smells like styrene, you actually can liberate a little bit of the free monomer just by breaking it. So that's kind of one of the weird things that you can see with styrene that actually is fairly unique to styrene. None of the other polymers seem to do that. Okay, then we have the last two are esters. Okay, so we have acrylic esters. So the acrylic part is the we have acrylic acid is a vinyl group with a carboxylic acid on it, and then we make them into esters. The ethyl ester is used a lot as the flexible polymer in paints, in latex paints in particular. A latex paint is a mixture of some liquidy polymer materials, some solid polymer materials, and a water with an emulsifier. So it's actually a water-based mixture that's all mixed together. And then as the water evaporates, it lays down and forms that water-insoluble paint layer. Okay. The last one I want to talk about here is called methyl methacrylate or polymethyl methacrylate. Polymethyl methacrylate is kind of like polycarbonate in the fact that it's used as a clear, transparent material. However, it's not as tough as polycarbonate. So polycarbonate is used for safety glasses, but methyl methacrylate's not, and it's much cheaper. You can see it at Home Depot. It's used as glass substitution. Hang on, let me grab a green tea here. Cold weather just doesn't help my cough at all. All right, so, but the thing that all of these have together is that they have that double bond. And that double bond is the part that reacts to make the polymer. Okay, so how do we make a new carbon-carbon bond with something like a double bond? We've added stuff across it, but we've never actually tried to make it into a polymer. So we're going to have to use a new mechanism that we haven't played with before that's called a radical mechanism. Now, a radical is a molecule or an ion with one or more unpaired electrons. Okay, why is it unpaired? Well, that's a high energy state, but the cool thing about radicals is once you form them, every time they react with a neutral species, they generate another radical. And so we call this a radical chain growth mechanism. Okay, so most of these are actually initiated. Oh, sorry, there's 3 steps in the radical chain mechanism. We have to initiate, and we usually initiate with something that is easy to make a radical with. And so it's something like a peroxide, which we'll talk about in a minute. The next step is chain propagation. And these are going to keep making new carbon-carbon bonds and making new radicals until you run out of things to actually react with. And then once you run out of things to react with, you get radical and radical coupling that terminates the reaction. So we initiate, we create a radical, we propagate where the radicals make new radicals, and then we end by taking 2 radicals and putting them together. Okay, so we'll go over each of those steps independently. Okay, so the first thing we need to do is we need to create a radical. Okay, so in all the reaction mechanisms we've done up to now, we've been using a 2-pronged arrow showing 2 electrons moving from one place to another. Our nucleophile had 2 electrons and we had a double-pronged arrow. When you create radicals, you must use a single-pronged arrow or a fishhook arrow. So notice right here when we have this here, we have a sigma bond between these 2 oxygens right here. And that sigma bond is 2 electrons, right? So if we want to break it evenly, such that 1 electron goes with each of these oxygens, it has to take 1 electron and a single-pronged arrow, the other electron with the single-pronged arrow, and that gives us this radical species here. Most of these initiators are using the oxygen-oxygen bond to generate that first radical. The reason is that both oxygens have the same nucleophilicity. They both want the electrons the same amount. So it's easier for them to break up into 2 radicals than to have one leave as a cation and one leaves as an anion. Most of the mechanisms we've done up to now, we've had that break heterolytically, generating an anion and a cation. Here, we're actually going to break it and generate 2 radicals. Okay, so those radicals are the reactive species that leads into the propagation step. Okay, so the first thing we do is we initiate it with something that easily decomposes to give us 2 radicals. Okay. Then we have to start a chain. So to start the chain, we have to take that initiator and react with something in the reaction mixture, usually something with the double bond, okay? So after we've reacted that, we have what we call the propagation step. And in this step, the radical initiator attacks one of the alkenes, and that generates a radical, which then attacks another alkene, which generates a radical, which attacks another alkene, which generates a radical, and it keeps going and going and going and going and going. Okay, so that's the second step, is the propagation step. So what does that look like? Okay, so our initiator is the thing with the radical to start with. And again, with the single prong arrows, we're going to use 1 electron from the double bond to make a sigma bond with the radical of the initiator, generating a new sigma bond here. Okay, so now, because we only used 1 of those electrons in the double bond to make that new sigma bond, we now have a new radical. That new radical can then reach out and grab 1 electron from another neighboring alkene, leaving a new radical. And then that one reaches out and grabs one electron, leaving one electron there, a new radical. And it just keeps going and going and going until you run out of double bonds to make those new radicals. Okay, so does that make sense that why we're creating these new carbon-carbon sigma bonds by taking one electron from an alkene and then one electron from the radical to generate a new radical. And then you just keep making carbon bond, carbon, carbon, carbon bond, carbon, carbon bond, etc. So also notice we haven't lost anything. We didn't lose hydrogen. We didn't lose water. We're just adding to our chain, continuously making those new carbon-carbon bonds. Okay, so this is the same kind of thing that happens when fatty acids oxidize and free radicals form. That is the reaction of forming the radical is that it basically oxidizes somewhere with the ester linkage that's the part of our fatty acids, and then you get a per acid form at the end, which breaks down and gives you a radical. So propagation is self-perpetuating, or does it require a catalyst? Good question. Propagation is self-propagating. You do not need a catalyst. You need to initiate your initial radical, but that radical is just going to keep going until you run out of double bonds to play with. Okay? All right, so then the last thing we have to do is you're going to terminate the reaction. And so there's a couple ways to do it. If you have, if you run out of double bonds, then eventually a radical at the end of one chain is going to come along with the radical at the end of another chain and make a final carbon-carbon bond, one electron from each, meaning you do not generate a radical. So now you have two radicals reacting together to give you a neutral species, and that ends the radical chain. Okay, so now you have no radicals and the reaction is complete. Okay, so initiation to generate a radical, propagation generates a radical, termination takes two radicals and makes a sigma bond. All right, questions on that? Okay, so this is a really different mechanism than anything we've done before. So I wanted to make sure you asked some questions there. Okay, so within that radical growth mechanism, we can find that there are certain biases as to how it's going to react, okay? Any of these radical reactions that we start with double bonds almost always give a more stable or more substituted radical. Radicals are like carbocations. The more substituted they are, the more stable they are. So that means if our initiator is going to come in and react on this side or this side, it has a choice. If it reacts on this side here at the number one carbon, it generates the secondary radical. If it reacted on the number two side, it would generate the primary radical. So it will preferentially leave the secondary radical, it will preferentially form the secondary radical. Now, that secondary radical will preferentially attack the number one carbon of the next molecule over. So because we're doing that, we actually have a particular way the polymer lines up. We call this head to tail, okay? So you can call either side the tail, and I'm gonna call the R the tail right here, which means the head is the number one carbon. So the radical is always gonna attack the tail, leaving the radical next to the tail. That tail is then gonna react with the head of the next molecule, and that tail is gonna react with the next molecule. So it preferentially runs that way. So whenever you try to figure out which way to add these together, you're going to try to always form the more stable radical, and radicals follow the same stability trends as carbocations. Tertiary carbocations are more stable than secondary carbocations, and that are more stable than primary. Okay, so the first commercial polyethylenes produced were by radical polymerization, but were soft and were kind of sticky, okay? And so then they were able to change it a little bit to, what they did was they put some branches in there so that our groups were at different lengths. So we'd have a methyl group or a hexyl group or a thing. When they were able to make those, change the mechanism so that they had branches, it became tougher. And that because those branches don't let those chains pack as tightly, it's called low density polyethylene, or LDPE. Okay, so if you ever look at like a recycle code, you have low density and you have high density polyethylene. Low density is when you have a lot of branches. Okay, so how do they get the branches? Do they put just a bunch of different types of monomers in there? Well, no. What they can do is by changing the mechanism slightly, they can increase the branching by transferring the radical from one chain to another. So because of this lower density, they are largely amorphous, less crystalline, and they are largely more transparent. Remember when we talked about crystals and crystal packing? The more crystals you had, the more scattering of light it would have and the more opaque it is. This has fewer crystals and becomes much more transparent. Okay, so approximately, think about when you go to Lowe's and lay down plastic for when you paint or something. That's a fairly clear, transparent polymer, and those tend to be largely amorphous. Okay? It's used a lot for baked goods and wrapping of vegetables, and sometimes in trash bags, but they put fillers in trash bags so that they can be a little tougher. So they're usually not opaque, or they're usually not transparent. Okay, so how do we make these sheets of film? Well, one way to do it would be actually melt it and then pull it out of a film die that would have it be that. But that's very hard to make a really wide sheet because you're trying to spread it out. So they actually have a cool trick. What they do is they take the polyethylene as little pellets and push it into a heater. And then they push that into a die that makes a round tube, okay? Now it has a round tube and it's fairly thick. And so what they do is they push in hot air and that blows up the tube till it gets really thin. And by controlling the pressure inside this bubble, it tells you how thin your tube is going to be and then how wide your sheet is going to be. And then at the end, it rolls them together after it's cooled enough that it won't stick to itself, and then it rolls it up into a sheet. Notice when it's first formed, it's formed as a tube, okay? And to make it into sheets, they actually have to cut a line somewhere along the system. So that's a good way to make that low density polyethylene film. It's transparent, it's mostly amorphous, and it is lower density and more flexible than other polymers. Questions on that? Okay, so let's talk about how they do that change transfer. Okay, so instead of having that radical react with another monomer somewhere, what can happen is it can transfer the radical into its own chain. Okay, polyethylene is made with ethylene, right? And you only have a primary radical on one side or a primary radical on the other side. That's the only way you can form it, right? But we know that secondary radicals or tertiary radicals are more stable. So what happens is it bends around and pulls off a hydrogen from somewhere in the middle of the chain, generating a second radical, a secondary radical, sorry. One radical, but a secondary radical. Now that secondary radical, it was more stable. That's why it did it. And so now what it'll do is it'll grow from that point on, giving you a longer polymer. But whatever length of chain wrapped around and touched the other side and took away that hydrogen is now the chain coming off, okay? So it's really common to make a 5-membered ring or a 6-membered ring or an 8-membered ring when you do this. So your chains tend to be butyl branches and hexyl branches and octyl branches when they do it. All right, questions on the chain transfer reaction. Okay. The driving force is to make a more stable radical, and that more stable radical makes a and that tail hanging off the polymer makes the polymer less dense. Okay, so, but that's not the only way to do it. If you want to be more precise and not have this backbinding happen, then you need to change the mechanism. When we change the mechanism away from this radical polymerization, we can do it where we grow it specifically from the surface of a catalyst, okay? And we call this the Ziegler nada polymerization. It's still chain growth because we're growing from one end to the other and only making carbon-carbon bonds, but it doesn't make radicals, okay? So these catalysts, these Ziegler nada catalysts, are what we call heterogeneous, meaning they don't dissolve in the reaction mixture. They are solids that are on top of little particles of magnesium chloride, and then they add a metal like what we call tickel chloride, which is titanium tetrachloride, and then you react it with an alkyl aluminum material. These alkyl aluminum materials actually are fairly toxic, so you want to use as little of these as possible. And so when they create these, they create them in these big batches and big reactors, and so nobody ever touches them. Okay, so the way it's different is, number one, we're not forming a radical. Number two, it starts forming the polymer at the surface of the catalyst, okay? So the first step is we take the magnesium chloride and react it with titanium chloride, and it adheres to the surface. So now we have a titanium and a chlorine sticking off the surface of our magnesium particle here, okay? Then we substitute the chlorine off with one of the groups on the aluminum, alkyl aluminum complex, and that generates a first part of the chain. In fact, it makes the end of the polymer chain. Okay, so now our particle has been activated and we've started to do the polymerization. Now, that titanium carbon bond is reactive enough to insert another molecule of ethylene in between the titanium and the carbon bond. So this was the end of our chain, and we just had the next monomer unit add to it. But we didn't generate a radical, so there's no backbinding. Okay, so then you can just keep inserting ethylenes in between this titanium and carbon bond until you get very, very long chains with less branching. Okay. So because there's very little branching in these things, you get to have the long polymer chains are big and have a lot of surface area. So there's a lot more van der Waals crystallization happening, van der Waals interactions happening. And there's very little things to keep it from packing really nice and tight and becoming crystalline. So in high density polyethylene, they tend to, number one, be more dense material. Number two, they are more crystalline, and they tend to be much, much stronger than low density polyethylene because we have all those van der Waals crystals giving it material. Now, because it has a higher melting point and a higher density, and it's more crystalline, most of the high density polyethylene is used by blow molding, and it's used for containers and stuff like this. This is actually a polyester, but I'm sure we have somewhere. Okay. So there's also a special fabrication process to help adopt the completely extended chain. And when they do that, they have perfect polyethylene, so there's no branches at all. And then they pull it as it cools so that you can, like nylon, make it more and more crystalline, and then these become very tough. This is called spectra fiber, and it's also used in some forms of bulletproof vests and used in like belts in cars instead of steel. They're very, very tough, just like Kevlar or just like nylon. Okay, so what does blow molding look like? Well, we use some of the same things we used in the last one. We're going to use some kind of mold. We're going to heat up our plastic, and then we're going to blow air pressure into it. And when we do that, it it blows to the sides of the molds, and then it cools. But by the time it hits the sides of the mold, it's cooled enough so it doesn't stretch or flow anymore, and then you can pop it out of the mold. Okay, so this is what we call blow molding. So most of the bottles, like water bottles, are blow molded as well, and the blanks actually start looking like these little things with the threads on them. It grabs the threads, heats the bottom, and then blows it into whatever shaped bottle you have. Right. Question on high density polyethylene. Okay. So we see the reaction mechanism difference between low density polyethylene and high density polyethylene, but they're both still chain growth mechanisms because we're inserting into double bonds, and we're making carbon-carbon bonds without losing any small molecules. Okay. So if we think about all the different types of polymers we use readily, they have recycle codes, okay? So recycle code 1 is what we call PET or PETE, which is polyethylene terephthalate. And think about, disposable drink bottles, lots of textile fibers, some of the shinier windbreaker type jackets are made with the polyethylene terephthalate. It can also be used in some kinds of carpet. The pet resistant carpets with polyethylene PET, or some polyester carpets tend to have polyethylene terephthalate, okay? But when you reuse them, you rarely use them for what they originally were done because it changes their properties slightly. Although PET is one of the ones that can almost be reused about 3 or 4 times before it loses enough properties to make it not useful. Okay. So the next one is recycle code number 2. Recycle code number 2 is high density polyethylene. Okay, and I can, let's see, high density polyethylene, that's mainly used for milk or water jugs where you start to see it starting to be a little opaque, but you can still see through it a little bit. Grocery bags are high density polyethylene, sorry. Oh, no, trash and grocery bags are low density as well, good. And bottles, so think about that, the jugs are tougher than the grocery bags because they're a little bit thicker and they're a little bit cloudy, okay? Once you recycle those, you can also do big containers like there's big drums of water near exits and to help you from hitting the main exit. Those tend to also be recycled high density polyethylene. Okay. Code number 3 is called PVC, okay? Now, most of the time for consumers, we don't really recycle the pipes and stuff like that, but shampoo bottles that have to hold materials that are a little more reactive than water can be made out of that. The shower curtains, if you've ever opened up a shower curtain and you can smell it, where it smells all chemically, those are the plasticizers they use to make the PVC really soft. Vinyl siding is mostly polyethylene with just a few fillers, no plasticizers. Wire insulation, floor tiles, and credit cards, unless you have an Apple Card, which is made out of titanium, which I do. And then when they recycle them, they turn them into floor mats and bed liners because the polymer degrades a little bit and can't be used for those same purposes. Recycle code number 4 is low density polyethylene. Think shrink wrap, grocery bags, plastic bags, and the squeeze bottles. Okay? And they can be recycled into trash bags and grocery bags. Polypropylene, remember, it just has that methyl group hanging off it. Tends to be a little tougher. Plastic lids, fibers, bottle caps, and the diaper lining, not the actual part that absorbs water, but the part that protects the water side from the outside world. These can actually be mixed together with a number of different things to make into stuff like Trex decking or pallets that look, any kind of plastic material that you can actually see things kind of waving through it. Those tend to be the recycled polypropylene systems. Code number 6 is polystyrene. Those are styrofoam cups, egg cartons, anything, a lot of plastic utensils are done that way. And then once you recycle it, They don't really like recycling styrofoam very much because it's just too bulky, but you can recycle it and used into trash cans and trays, Frisbees, and I don't know if you know what video cassettes are, but that was that old thing that used to use to watch TV before they had DVDs and streaming. So, anyway, I think I need to update that slide. And number 7 is everything else. Okay, so everything else that doesn't meet one of those demands, and most of the time they are turned into stuff like Trex or outdoor gear, or even stuff along the sides of the highway like road reflectors. Okay, questions on the recycling codes for plastics? Okay, so that is the end of polymer chemistry. That's all we need to know about polymers right now. All your homework is due before our next exam, so don't forget to do that before our next exam. And we will have our review session next Tuesday. But what I'll do now is I'll go ahead and stop recording, and we can stay behind and ask questions.